Last speaker for this session is Rafael Oliveira. Do you
Yeah, a little bit, however you want.
From Clemson. And it's going to take a slightly different
Yes.
topic, but it'll be fun.
Thank you, everyone. Thank you, the organizers, and thank you, everyone, for being here. So I'm going to talk about secure distributed matrix multiplication. So the setting for this problem is quite simple. You can imagine a user who wants to multiply two matrices that he has, and he wants to do it quickly. So he wants to use the help of servers to accelerate the process. However, these matrices might have private data or be correlated in some way to some private data of his. And so he would want to do this in a way where the servers do not learn anything at all about what is in the matrices. So one of the applications for this could be in a training some type of machine learning model where these matrices are generally correlated to your data in one way or the other. And you would want to, so generally the matrix multiplication is the most expensive procedure in many of the algorithms that are used. So here for security, we're looking at information-theoretic security, and we have this parameter T, which controls the amount of servers that we are permitting to talk to each other, or that we are hoping. Well, the scheme doesn't assume that they're gonna talk to each other, but the point is that if they end up knowing about each other, it's not good for us, and so there's this parameter T that controls that. And again, the goal is to speed up the computational time of this process. So Tandon and Chang were the ones who first looked at this in this more information-theoretic communication type way. There's been a lot of work on this. I'm just showing some stuff. In particular, maybe for the general audience here, this work by Vestimer on showing how to use this for machine learning type application might be interesting, just to see how this works in practice. We also did work on this for distributed learning on these like Android devices, although here the goal was not to accelerate, it was to lower energy costs. So you can think of it like you have your little phone wants to do a machine learning task, or your smartwatch, and there are these base stations and you use them and you want to save the power on your phone or watch or so on. There's also some interesting work by people here also on the differentially private version of this problem. So that seems to be exciting. And yeah, so this is some of the literature. So going back to our problem, I'll show the simplest way of solving something like this, and then we'll talk about how one can extend that. So the simplest way to go about this is using polynomial codes, or what could be some sort of like generalized version of secret sharing. And so the idea is that you take, so for this setting, we're going to have our matrices A and B, and we'll have three servers, and we'll just assume that the servers don't know who each other are, so they don't talk to each other. And then the idea is that you generate some random matrices, which are going to work as random keys, and you generate these polynomials. So your A plus Rx, your B plus Sx, and evaluations. So the X, you can think of it as a scalar, so that you're going to send evaluations. So the user will send evaluations of these polynomials to each one of the servers. So server one gets A plus R, B plus S. So he doesn't learn anything about the matrices A and B because they are essentially padded by these completely random matrices R and S. And the idea is that the servers are going to multiply these things and send them back to the user. Now, when the servers do this, it's as if the servers are evaluating another bigger polynomial, which is the multiplication of these two polynomials. So it's this polynomial here. And you can see that the answer that we are interested in appears as one of the coefficients of this polynomial. So this polynomial being of degree 2, you can then, if you had 3 evaluations of it, so this is what you essentially get here, so they're essentially sending evaluations, the servers are sending back evaluations of this polynomial here. With 3 evaluations, you can essentially retrieve all the coefficients of your polynomial, which retrieves what you are interested in. And so this is one way a problem like this could be solved. However, now, and this is the basic fundamental idea behind many of the other solutions. The point here is that if you look at what is the work going on here, all the servers are essentially doing the same amount of work of a full big matrix multiplication. It's not completely useless. You could have a setting where, like I said, even the user wants to save energy or something, and he just wants to outsource it. But in terms of speeding up computations, if even all the servers have the same power here, it's just going to take you as much as doing a matrix multiplication plus a bunch of coding and decoding. So to deal with that, you generally want to break up the matrices into pieces. So one way you can do it is through an outer product partitioning, which is you break your matrix into pieces. So these are all matrices also. You just broke it into sub-matrices. So you break it into this way. And so this isn't because it's an outer. One could also break it into an inner product or other types of products. I'm just going to talk about the outer product here. We do have work on the inner product stuff, but not enough time to talk about it here. So for outer product partitioning, you can think of it, you break your matrix A into these K pieces, your matrix B into these L pieces, and now you have a bunch of these smaller multiplication tasks that need to be done, and you can think of it in some way as if the servers are going to do 1 over KL of the work, and hopefully the idea is that when you distribute this whole thing, the whole procedure will take less time than just doing it yourself. That's the baseline for this, just do it yourself. And that's what we're going to look at. Okay. So the first thing, so again, in the previous example I was showing was essentially when K and L are equal to 1, where you don't do anything, you didn't partition it. Now, what is going to change when you start partitioning things into pieces? Well, the first thing is that you can't choose any polynomial. So before we were sort of lazy about it, where you just added a polynomial with a key and you put an X there and everything worked out. And here, if you try to do the same thing here, so let's say here we partition into 3 pieces, and we're going to do, at most 2 servers are allowed to talk to each other. So you have, that's just going to tell you how many keys you have to have here for your randomness, right? So if you're just lazy about how you choose the exponents here of your monomials here, this will not work out, because you need to retrieve each one of these individuals, AI, BJ. So you need to retrieve each one of these to get your full matrix. And you can see here that you will retrieve, for example, if you retrieve the H matrix here, the H polynomial, you will retrieve A1, B1, but you're not going to retrieve A1, B2 because there's going to be some noise from another term that sort of got mixed up with it. So you can't just be lazy about it. You got to do some level of design. Maybe the simplest level of design is this scheme here, where what you do is, so you're sort of lazy about your F polynomial, but the G, you sort of space out the exponents. So you can see here that there's not going to be this interference anymore, because now A1, B1 appears with the exponent 0. A1, B2 is going to appear with the exponent 5. And you're not going to have any other exponent 5 appearing. You can check that if any multiplication here, so A2 with this guy is going to give you an exponent 1. You don't have any exponent 5 interfering. So you just spaced out the exponents down here, and you don't have any interference. And well, so this could be one approach that one could take. And it was one of the ways that this was being looked at, which was essentially trying to minimize the degree of the H polynomial, because the idea was, well, when I was talking before, I was like, oh, it had degree 2, so you needed 3. So if you want to have the minimum amount of servers, well, then just minimize that degree of the polynomial H. And what we're going to see here is that that is not actually the case. So one could come up with this scheme here, which is a little bit more funky. It's not as simple as the one above. And you can check again, if you just break it all out, that you're going to be able to decode. There's not going to be an interference. A1, B1 is the only, he's going to appear with exponent 0, and nothing else is going to appear with exponent 0, and so on. A1, B2. So you'll be able to decode everything. he's going to have, so when you multiply these two guys, you're going to get a degree, a polynomial h that has a degree of 22, which is larger than the degree above. However, what's going to happen is that this h star polynomial here is going to have gaps in the degrees. What do we mean by that is there no terms appear, for example, with an exponent 13. So if you multiply this out, there is no term. So you can just look at the sums of the exponents. There's no term that's going to appear with a 13 or a 14 or a 16 or a 17 or a 20, which is equivalent as if you already knew that there's a 0 there. So you can, so that sort of means that you have like extra information about it because of the way you designed it. So you actually need less servers or less interpolation points to retrieve what you get, what you need. So if you do out the math, and so if you subtract these points from the 22, that means that in the end for the h star polynomial, so for scheme 2, you'll actually need 18 servers instead of 19 servers for the other one, even though the degree is higher. So just to make the point that it's not about the degree, which then takes us to the question, well, what is it about, right? And the idea is just what we talked about. It's about the number of terms or non-zero terms in the polynomial. And an easy way to see that is that if I gave you a polynomial of this kind, ax to the 6, bx to the 5th, cx, you wouldn't need, I mean, obviously with 7 evaluation points, you would be able to retrieve a, b, and c, but you don't need 7 evaluation points. You can do it with 3. It can't be any evaluation points if you get f. So any 7 will give you everything. Now you start to have to be careful about which evaluation points. So if you evaluate at 0, you're not going to learn anything about a, b, or c. So there are these extra points, but the point is that there is a way for you to retrieve it with 3 evaluation points. So now, so what does this say about the general problem? So how can we do things with this? Yes.
Question. So let's say you have sparse polynomial, sparse in the sense that the number of terms is less than the highest degree.
Yeah.
And you said you can, of course, retrieve it with fewer number of evaluations. But at the end, you don't even need all the terms of that sparse polynomial because you're only interested in some of the terms,
yes,
and not the others.
Yes.
Could you reduce it even further?
Yeah. So that's an interesting point. We don't know good tricks for doing these reductions for this outer product. For inner product constructions, there are tricks for doing that by evaluating at roots of unity. And there you are able to do these tricks where essentially you're able to match even more together the noisy terms that you don't care about. But I do not know of any roots of unity trick, and it seems to me like there probably isn't, but there for the outer product partition. But I would love to see a roots of unity or any type of field trick for this problem, for the outer product version. Okay, so let's solve the problem in general. So again, you broke it into 3 by 3 pieces, and you had 2 guys, and it's about essentially choosing these alphas. So now, what do we want to do? We want to, so the point here is that the h polynomial, the exponents that appear in the h polynomial are just going to be related to the sums of the exponents that appear in f and g. So this is what we call a degree table because it's essentially taking the degrees of that appear and just summing them up together. And the point is, can we then just look at this table here and just by looking at this table know, like solve our whole problem or understand our problem? And so the way that this works out, so if you take again so what properties do they have to satisfy? If we take our nice f star and g star polynomial, so what was happening, here you put the exponents of the f polynomial here. So here are the exponents of the f polynomial, here are the exponents of the g polynomial or the g star polynomial, and the h star polynomial is going to have terms with these exponents. And what's going to happen is for the codability, you're going to need the red cells here to be unique because they correspond to the things that you want to decode. So this 0 here corresponds to the a1, b1 appearing in the h star with an exponent of 0. This 3 here corresponds to the a1, b2 appearing with an exponent of 3. And you can't have any number outside or anywhere be the same, because you would have this interference happening. So guaranteeing that this red region is unique is enough for you not to have this interference phenomenon. For the security, one can show, I'm not going to show here, but one can show that you just need to choose these numbers here to be different. They can, so then there's no problem with the 9 appearing here, but this 9 and 10 have to be different here. The idea is that if this 9 was equal to this 9 here, it's as if you wouldn't have 2 keys, you just have one of them together. So, but it's sufficient to just have separate keys is enough. And these are it. These are the properties that you need. So given that, the goal then is just to minimize the amount of distinct, because these are going to be the exponents that appear near h. So the amount of these distinct exponents is just what you want to do. If you minimize this number, so if someone here from the audience makes a table with numbers here, so choose some integers here, choose some integers here, make them satisfy these 3 properties, and have them have less distinct numbers than what we have here, let me know, because this is the best we know. So you just beat us. And very simple, just any high school kid could sit down, it's just addition tables and check these things easily. Okay, so essentially what we've done is we have restated this whole secure distributed matrix multiplication problem into some fun combinatorial problem, which just has these tables. So just to restate then, the goal is that if you give us how you want to partition your matrices in this outer product form, so if you give us these parameters k and l, and what's the security parameter t, then the problem is find integers. So find k plus t integers here for one of the polynomials, l plus t integers here, such that when you just do the sum table of them, these guys are unique, these guys have to be different, these guys have to be different, and the goal is to minimize the amount of distinct terms, and that's it. If you do one that's better than another one, it's easy to check which schemes are better. Okay, so let's construct some schemes then. So the first scheme I'll show is what I believe to be the laziest scheme, and I'll show why. Because we just put the numbers, they have to be different, 0, 1, 2, and just put a 0 there, which, so you're going to get a 0 here, a 1, a 2. Now the next number you would have to put up here, it can't be 0, 1, or 2, because you would have just a repetition happening here. So just lazily go for the next number and continue to do that. Lazily go for the next number, continue to do that. Now for again here you can't, so now the numbers from 0 to 8 you can't use them anywhere, so just go for the next number, 9 there. You can repeat it there and don't even think about it, they just have to be different, just make them different one after the other. And this is a scheme, here I showed it for k, l, t equal to 3, but it's easy to see how you can generalize this, just do this construction, and this is called GASP big. And the next thing, we'll get back to that. So you can then calculate how many servers you're going to, so n is the number of servers you'll need, and it's related to the number of regions in some way. So we can solve that. And the nice thing is that when we came up with this, so here it's number of servers versus security level, less servers is better. So you want to, so down is good. So this GASP big construction was already very good when it came out. It's still very good for large T. It's the best for large T under these parameters. But and so the point is that, okay, so that gave us this idea that the degree table is nice in some way. I mean, even lazily solving it, you could do well. And then the idea is, well, so what's good about this construction, right? About this GASP big. And the reason what's good about it is, so you want to have a lot of repetitions outside of this red region. And the way that it works is that you have these diagonals here that you can see of repetitions that appear. And they're also appearing here, right? You get these 1919, 20, 20, 20. And the reason these diagonals appear is because of these, it's because this is an arithmetic progression with difference 1. And this is also an arithmetic progression with difference 1. So you get this diagonal, like every time you go one here, it's the same if you had gone one down here. So you get this here. This is sort of a mess because you get like, this is also an arithmetic progression, but difference 3 versus 1 here. So it's sort of, it's as if you sort of sacrificed this part to get a lot of repetition here. And when t is very big, you're going to get this part very big. So there's a regime where this part is very big, which is when this scheme will do very well, which is why it does very well for large t. But the point is that there are regimes where this is very big. And so one could potentially be like, well, maybe I can then improve for that. And you can by doing so. Of course, if there's gas big, there's gas small. So it's for small t. What's going to happen is instead of, so do the same thing as before for this part here, and you get your nice repetitions here, no problem. But instead of focusing here, focus on this part. So now instead of trying to match this arithmetic progression, match this one, which is 3. So you start with the 9 just to get, because you get for free some repetition, but just go by an arithmetic progression 3 here. And now here you get the diagonal stuff. And you sort of sacrifice this part. But then for a certain regime, it'll do better. Of course, this is just an example, but you can make these curves be as far as you want. But the point is that, so the gas small will do better in the beginning. That's why it's called small. It's for small t. And then at some moment, the gas big will do much better. Okay, so you can find bounds on this problem. So and I don't have much time to talk about how you find the bounds. They're not too complicated. They're also sort of lazy in some sense. However, they do give you two things, which is nice. They give you optimality in the beginning, and they give you order optimality. So you're never twice away from the optimal towards the end. So you end up with sort of like, okay, so what's going on in the middle, right? Can we optimize in some way in the middle or do better? And so there is a generalization. And if before we were using arithmetic progressions, you just use generalized arithmetic progressions. So this is gas small. So remember, gas small was the one where we make this guy match with this guy here. So arithmetic progression 4, and you get the diagonals here, right? This is gas big, where you just make this match here and you get the diagonals here. But you have sort of like these intermediate guys where you sort of do, this is called a generalized arithmetic progression. Instead of jumping here like by 4s or jumping by 1s, you do this thing where you first jump by 1, then you jump by 4, and then you do a jump by 1. And this one is like you do, 2 jumps by 1, and then you do a jump by 4. And they sort of get these intermediate type things where you don't necessarily sacrifice too much from one side or the other. And so for this particular example, k, t, l equal to 4, the GASP2 here, this one has 36 servers. He actually does better than either one. Oh, he wants to do something there. Sorry. Sorry. So it is the case that there are these intermediate regimes that do better. And you have this sort of situation where the GASP1 will do better, then the GASP2 will do better, then the GASP3 will do better, and then the GASP-T will do better all the way forever. And for outer product, regular partitioning, this is the current situation in terms of what's best. The bound is not tight because you can actually, so we also have results in terms of you can transform the problem into a binary linear program type search problem, but it's like infinite because potentially your numbers that you could choose could be infinite, right? But for certain cases, we can actually show that, oh, the optimal guy is not going to be like some infinitely large guy. We can show that it's like, oh, if you have this inequality being satisfied, then the numbers that you choose will never be larger than this, and you can make it into a finite search. And then for those parameters, so for example, for k equal to l equal to 2, we can actually, and t equal to 5, we can actually make it into a finite search. And for the finite search, we can then see that GASP2 is the optimal. And for this particular case, it doesn't match the lower bound. It's going to be an in-between point, which shows that the lower bound is not optimal. And yeah, we've run a bunch of searches, these computational searches. We've found a lot of things that tie with the GASP-R stuff. We've never found something that beats it, but there are things that tie with it and do not look like it, which means that maybe there's something there, you know, and so on. I guess the last thing I'll comment is, okay, so I was talking about you doing all of this, and then there's the problem of, oh, well, is it worth it? Do you actually save, right? So going back to the speeding up computation, right? It's not the case that it's always worth it. And this is something that one needs to be careful about. So the idea is the following, is just to make everything two-dimensional, if we fix our matrices to just be n by n matrices, and let's make the security parameter some constant. And now let's say that you multiply two matrices in time n to the omega, and for this graph here, that omega equal to 3 is the usual multiplication. So let's think of just doing the usual multiplication. And now there's a partitioning parameter. So K and L is how much you partition the matrices. Now there's a parameter epsilon saying like how much you want to break it up. So you can think of epsilon saying how much you are going to break up your matrices. So the higher epsilon is, the more work for the servers and the less work in some sense for yourself in terms of the multiplication. Now what's going to happen is, so if you locally did the computation, you could always just, I mean, this is just the baseline. You're just locally doing something that takes cubic amount of time. Now, what happens is that as you start to break up the matrix into pieces, you can lower, this is the total time complexity, including communication. So it includes everything, encoding, sending it out, they do the multiplication, they send it back, you do the decoding, it's the whole time of the whole procedure. So what's gonna happen is that as you break up the matrices into more and more pieces, you can lower the total time complexity, but there's a minimum. And after that, it starts to get worse, and it can actually get worse than what you were doing. And the analogy here is, that, so you can think of it, so in this point here, it would be you break up the matrices so that each server is just doing an inner product. So if you did that, each server would be happy. They just have to do nothing, like a linear operation. But you have to contact so many servers that your decoding is just going to take longer than just doing the matrix multiplication yourself. And this is an analogy with real life. Like sometimes if you're going to ask help for a bunch of people, it can't be that coordinating them takes you more than just doing it yourself. So there's a sweet spot there. And this can be calculated. And you can get, so for example, if you're doing like cubic complexity, if you do the optimal, you can lower it from like cubic to the whole system doing it at 2.5, right? And so, and if you were to use Strassen, you can also lower it. So you get this like optimal curve. In practice, these 2 points are the thing, with this one being heavily what's used, but there's more and more Strassen being used. These, like something like this is for matrices that are so big that we don't know how to implement this in efficient things. But the point is that it can be worth it if you choose correctly. There has to be some care on how you choose the breaking of the stuff. And I'll just leave some open problems. Like I said, bounding the entries of the degree table could be good to solve, like we said, the problem with this integer programming approach. We were doing it through polynomial schemes. People haven't, is this the best way to do it? Is there some other way to do it? I know linear ways to do it, but they don't beat, they tie with the polynomial. I mean, polynomials are linear, so by definition, they have to tie, so, but they tie. Is there a non-linear way of doing this? I've never seen, I would love to see. Even if it were worse, just out of interest, I would think it would be very cool to see. General bounds. And this one, can extra computations help? So here we're just making the servers, they just multiply and do nothing else. If they do something extra, can it help? I put this here because for inner product, we have work where we show that it can help. So you can do these things where you actually do some extra stuff and it helps out the whole system. But for outer product, what I talked today is the best I know. I don't know how to do any better than what I showed you guys today. So thank you.
So we can make questions.
So, so that lower bound that you showed, is
Yes.
that specifically for the polynomial scheme?
Yes, for the degree table approach.
Okay, okay.
For this
Really
precise
specific.
approach, yes. So the way that this works is you can, so what we're doing here, so there's this area of combinatorics that worries about sum sets. So you have like two sets, finite sets, and the sum set is all possible sums of them, which is essentially what this table is. It's a sum set. And in the sum set theory, they think about like, oh, okay, so you want to control the size of, and if you just have two sum sets and you want the best size, you just do an arithmetic progression, and that's the best thing to do. This is a weird sum set because we have this very weird condition here of, for some reason, this block has to be unique, and that's why it messes everything up. So what we did is we took a bound from there, and we sort of like this has to appear, there's nothing you can do about it. We sort of bounded this with the sum set stuff, and we ignored this part, so it's sort of a lazy bound. And that's where our bound comes from. So it's a bound for this type of construction.
Information-theoretic lower bound. Yeah.
So that's a great question. So, because this problem has an issue for information theory, which is the following. And that's why, so I showed one thing that's called SDMM, right? And there are many problems that they call SDMM also. One of them, they make the initial user and the final user be different. And the reason is because there it makes more sense. It's easier to look at your question because since I don't have the information, there's an information question about how much I need to receive. But here, the uncertainty about A times B, given that I have A and B, is 0. So from a pure information theoretic perspective, there's nothing to be done. So because the whole point is that so there's a computational complexity issue, and if you even remove the security aspects, computational complexity of matrix multiplication is an open, very hard problem. This would be a generalized version of that. Like an answer to that question would be like probably an answer to even the other question, because as we saw, it even depends on how quick you can actually do matrix multiplication just yourself. If it came out that you could do it quadratically, then you can just do it yourself quadratically, right? So another interesting direction would be something of the form, like one could ask, so this is just things I've thought about, but one could think of like, oh, what's the entropy of like A times B given A and B, but conditioned on like a finite amount of operations. So some form of like entropy, but where I said like, oh, but you're only allowed to do, I don't know, 50 computations. You know, you're not allowed to do like an information theory, do everything. If there was a theory of that, which seems to be, would sound like a very hard theory because it sounds like a, you know, like it's like a Combinatorial complexity thing. Like, what is all the possible things that one can do with this amount of computation? And you know, when you understand what I mean, it's a complicated getting. So in that other version, when they're separated, there you can have more definite answers in that. Because then, yes, there's a precise question. So if you have a user, intermediate servers, and a final user who wants the computation. Since the final user does not have A and B, one can ask purely how much information needs to be sent to him so that he can get it.
Any other questions?
Are the lower bounds tight in that case?
Oh, so there's a complicated thing in that case.
You can talk later.
Yeah. I'll just say because you can do PIR tricks and that, like you can do things even with two servers, but they involve exponential amount of computation. What I'm saying is that you can do well by breaking the making the whole thing take exponential amount of time. You know, but now again, in that setting, it's okay to be exponential amount of time because user 2 does not have the information and you're just trying to minimize the computation. But yeah, but if you care about computation, yeah, it's not clear to me, but maybe the other one sort of reduces to a PIR-like problem.
Any other questions? I'm so sorry. Thank you.
Thank you.